Physics 2211K, Lab 2, Projectile Motion by Carmen Pham. Introduction. The purpose of this lab was to observe an object in motion and its differences in one model accounting for gravity and another model accounting for gravity and drag. We explored Newton's second law within this lab. What is Newton's second law? Newton's second law, also known as the momentum principle, states that the external net force is equal to the system's change of momentum divided by the time over which it occurs. And you can see the formula down here. F net is equal to the change of momentum divided by the change in time. Using that formula, you can get to the momentum update formula, which is P final is equal to P initial plus F net times the change in time. And using that, you can determine the velocity update formula, which is V final is equal to V initial plus F net divided by mass, and times all of that by the change in time. Procedure. For this lab, we first recorded a video of an object that is thrown in projectile motion. We then uploaded the video into Tracker and determined the object's initial position on a frame-to-frame basis, and this was our observed position. We then developed a computational model. This was our predicted position on GlowScript, using making one including drag and one without. We used the data from Tracker to help make our computational model. We then graphed the models, the observed position, predicted position with and without drag on Excel. Initial conditions. The mass of our object was 0.0045 kilograms. Our object's initial position was 0, 0.51, 0 meters. Our object's initial velocity was 2.78, 2.18, 0 meters per second. Our F drag was calculated by using the formula negative B, V squared times V. The system was the paper ball, and our surroundings was everything else, the earth, the surface, me, etc. Assumptions. The force of gravity is constant, the equation of F drag, and motion was only in the X and Y direction. This is our experiment. As you can see, the ball was thrown in projectile motion, and it changed in both X and Y directions. And seeing the data down here from Tracker, we used that to graph in Excel and determine our initial conditions. This was our code. We determined that we know that the ball's mass is 0.0045. We inputted the initial position, the initial velocity over here, and then our time is equal to 0. Our delta was 0.033, which is the time of each time step that we used in Tracker to on a frame-to-frame basis. And then our gravity constant was 9.8. Our B value was 0.000121, and we got that value by trial and error. And then while t is less than 0.7, which is the time of our whole projectile motion. And then down here, we have the j hat vector. And then we determine the force of gravity by using the F net formula, and then the force of drag by using the force formula again. And then we found our total F net by adding our force of gravity plus force of drag. And then down here we have our velocity update formula, and then we have our position update formula down here. The same thing goes with the predicted position without drag. However, the only difference is that our B value is equal to 0, because when B is 0, that means that there was no drag at all. And as you can see, our GlowScript analysis, here's our graph with the drag, and this is the graph without drag. You can see that the graph without drag is wider than the one with drag. And these values were given from GlowScript. Data comparison. All three graphs were displayed here. You can see that the one with predicted with drag is most similar to our observed position, which is our actual data that we got from Tracker. And then the one that we predicted without drag is not similar to the observed position at all. So you can see that with drag is more accurate. Discussion. The model that accounts for both gravitational and drag force is more accurate when it comes to predicting motion. The computational model without drag overestimates the change in position, and the possible sources of error include human error using Tracker, or the drag force could have been inconsistent. Questions to consider. What models, if any, predict the terminal velocity? Terminal velocity is achieved when the drag force is equal to the gravitational force. The model that includes drag predicts the terminal velocity because if the object fell long enough, it would eventually have a net force of 0. As you can see from the graph, the slope starts to change and flatten out, becoming more linear towards the x-axis. You can see that there's a curve right here and how it starts to curve towards the end right here and flatten out. Imagine that object was initially thrown straight up with the same initial speed as used in the experiment. An object thrown straight up with the same initial speed as opposed to a projectile motion would take longer to reach the ground due to having to fight against gravity. The object would rise higher, thus taking longer to fall back down. For the thrown object, some of the forces are acting horizontally. Thus, the upward motion is weaker and reaches a lower peak before falling back down. With gravity only acting on the vertical direction, the time it takes the object to reach the ground is much shorter. Thank you.